Sorry to cut off this fascinating conversation, but good morning, everybody. Welcome back to Calc 2. Plan for today is just got a little bit more I want to say about the gamma function and its relationship to the factorial. And then we're going to jump into Standard 8 and talk about arcing. Just so y'all know, expect Standard 8 to be take us. We expect to finish that up probably at the end of Friday's class, so we'll be ready to jump into Standard 9 and start talking about surfaces of revolution after the break. I've got my usual office hours over the next couple days. Today at 11 and at 1, tomorrow at 1. As far as homework goes, I posted a web work set, homework 12, which will be due Monday after the break. Give y'all some time to stew on it over the break in case y'all have exams or something going on next this Thursday or Friday. I don't know who would assign you exams this Thursday or Friday, only a cruel professor.
Capstone.
I laugh because I know of many exams that I've heard are taking place over the next few days. Speaking of exams, I graded the exams, and as well as Monday's quiz. So a few comments on exams. So keep in mind, if this exam didn't go as hot for you as you would have liked, this is not your traditional exam, meaning even if you only got like 1 or 2, or heaven forbid you didn't get any masteries on this exam, there's still plenty more opportunities to get your masteries, even on these earlier standards. There's a second midterm. There will be 2 more midterms, both of which will be cumulative, meaning I'll have questions from all of the standards 1 through 7, as well as more recent stuff on the next 2 exams. And also the final exam will also be cumulative, cover every standard. So if this exam didn't go for you, don't worry. Doesn't mean you've tanked your grade or anything like that. I just maybe try and take that as a wake-up call that, hey, you might need to start working harder, or you might want to come talk to me, see how, get some tips for how to do better next time. I have posted exam solutions on Canvas on the module page where I post all the other things that I post. Encourage you to check those out, and be happy to talk with you about your exam as well if you want to know how you can do better going forward. But with that in mind, does anybody have any questions or comments related to the exam? What would a mathematician call a couple of MDs? A mathematician would call a couple of MDs a paradox. Paradox. Okay, so last time we were talking a little bit about the factorial / gamma functions and their relationship to each other, where we said that for the factorial, the idea is if you want to take n factorial, given some positive integer n, we multiply out n times n minus 1 times n minus 2 times all the way down to 1. We multiply n by all of the integers between n and 1. And as far as the gamma function is concerned, we had that the gamma function, gamma of x is equal to integral from 0 to infinity of t to the x minus 1 e to the negative t dt. Where in general, if you want to evaluate what is the gamma function going to be equal to, you're generally going to want to do some integration by parts. Like if you wanted to find gamma of 2, you plug in 2 for x, integrate t e to the negative t from 0 to infinity, and see what that would give you. And towards the end of class, you will notice a pattern in the output values of the gamma function and factorials. Namely, we had this theorem that we proved that says gamma of n is always going to be equal to n minus 1 factorial. So for instance, if I wanted to find something like gamma of 7, which normally you would have to do integral from 0 to infinity t to the power of 7 minus 1 e to the negative t dt. And you would have to do 6 different integration by parts in order to evaluate that integral. Joy, do you want to do 6 different integration by parts? I don't really want to do 6 different integration by parts. 1 integration by parts is scary enough. But if we were given this integral and we wanted to evaluate it, say the integral of t to the 6th times e to the negative t dt, what we could do instead is using our theorem, say gamma of 7, oh, that's just going to be 7 minus 1 factorial, which is the same as 6 factorial, or 6 times 5 times 4 times 3 times 2 times 1, which comes out to 6 times 4 is 24, times 5 is 120, times 6, 720. And I just think this is really cool. This kind of gives us a way to take a particular type of scary-looking integral, which theoretically we could evaluate using standard 3 and standard 6 stuff, integration by parts coupled with an improper integral. But it turns out we have a shortcut method for evaluating these integrals like this. You can just use the factorial function. Holy moly. So last time I was trying to trip up James here in class. I was asking him a few different factorial values. He was able to give me stuff like 5 factorial and 0 factorial. He was a little bit stumped as to how you would figure out 1/2 factorial. Because you look at this factorial formula, you want to try and evaluate 1/2 factorial. It doesn't really make sense how you plug in 1/2 for n into this formula. Like, this formula really only makes sense if n is a positive integer. So how on earth would you even take the factorial of 1/2? It's a little bit unclear. All right, James, after we've had a couple days for ideas to percolate in your brain, do you have any ideas on how you might try and evaluate 1/2 factorial now?
Maybe use the gamma function.
Yeah, we can, by itself, 1/2 factorial doesn't mean anything. Trying to plug it into this formula doesn't make sense. But we could plug 1/2 into the gamma function and use the fact that 1/2 factorial, well, 1/2 is just 3/2 minus 1. And if we wanted to find out what's 3/2 minus 1 factorial, well, it might make sense to try and use this theorem and just say that's going to be equal to gamma of 3/2. Which, if we evaluate out, is going to give us integral from 0 to infinity of t to the power of 3/2 minus 1 e to the negative t dt. Uh, 3/2 minus 1 is just 1/2, so we could write this a little bit nicer as square root of t e to the negative t dt. All right, how on earth would we evaluate such an integral? Besides stare blankly and say, Dr. Gersel, it's Wednesday morning before break. Why are you asking such difficult questions to us? I said besides that, but fine. Mary?
Can you do integration by parts? Does that work?
We could certainly try. How would you propose we go about it?
You could set the square root of t equal to u, and then you could set e to the negative t equal to dv.
Okay. Let dv be e to the negative t dt.
Yeah.
Sounds reasonable. If we do that, we'll get v equals negative e to the negative t. Du would be 1 over 2 root t dt, which I'm going to ignore the fact that we're dealing with an improper integral for now. We'll fill in those details here in a second. So that would give us something like square root of t e to the negative t, negative out in front, minus integral of v du, negative e to the negative t over 2 square root of t dt. So Mary, does this integral look any easier to evaluate than that one does?
Not really.
Doesn't really look any easier to me as well. You've basically just taken the square root of t and put it into the denominator of a fraction, which unfortunately doesn't feel as easy. Now the problem is, if we were trying to evaluate something like that using integration by parts, we could do integration by parts to get something plus integral of t to the 5th e to the negative t, maybe times some constant. And that, and the effect of sort of subtracting 1 from the exponent here makes that a little bit easier to work with than the original integral was. The problem here is here we have t to the 1/2 power, and when we do the same trick, which ends up subtracting 1 from our power of t here, going from t to the 1/2 to t to the negative 1/2, going from t to the 6th to t to the 5th makes it a little bit nicer to work with. Going from t to the 1/2 to t to the negative 1/2, it's not really making it any nicer to work with. Be nice if we could only do like a half integration by parts to make the power of t go down by like a half instead of by 1. But unfortunately, that's not how the power rule works. Okay, so integration by parts isn't going to be super helpful for us here, unfortunately. It's definitely a good suggestion, though, Mary. I'm glad you suggested it, because that's how we handled these original ones. So it would make sense to try that, I think. How else could we evaluate this integral, this square root of t e to the negative t? No. Jonah, I see you smiling. Do you have any ideas?
I was gonna say use up, but I'm not sure if that works. I don't think it will probably.
Unfortunately, I don't think it does either.
No, I was
And if you try u equals square root of t, or u equals, say, like e to the negative t, the du term doesn't handle the other t part of the t part of the expression. The t part, I mean the t pose. Bethany?
Would it help if we put maybe the e to the t in the denominator?
Okay. Wrote it as something like square root of t divided by e to the t? Okay. Sure, we can do that. Does that make it any easier to work with?
Is there a way we could use like, I guess, like use sub in order to like convert our t to something better?
We could try. In fact, I did try that myself over this past weekend. And I just dug myself deeper and deeper into a horrifying hole of sadness. Anyway, I couldn't get it to work out. So, I've got a confession to make. This does not have a nice integral. We do not know how to integrate this. We can do, doesn't mean mathematicians don't know how to do this. It just means that we as a Calc 2 class do not have the tools to try and evaluate this integral. Turns out, comes out to square root of pi over 2. Which is really weird if you ask me. Because like 0 factorial is equal to 1, 1 factorial is equal to 1, you'd expect a half factorial to be, I don't know, something pretty nice looking since it's halfway between 0 and 1. Nope, 1/2 factorial is square root of pi over 2. But how do you, but where is pi coming from in this expression? Well, I'm not going to get into all the gory details of how you get pi that comes out of this somehow, but I'll give you a hint. It involves inverse trig. In a scary, horrifying, I think I already said that, sort of way. Any questions or comments? If you go talk to if any of you know Dr. Webster, guy's office is right next to me. This way, goofy guy, loves his baseball. The area of math that he studies is called numerical analysis, which kind of studies how can you approximate integrals like this that we don't have nice ways to evaluate. And believe it or not, most integrals that are out there in the wild, because there's integrals hiding out in the wild, we don't know how to evaluate. So for instance, if I were to ask you how to integrate e to the negative x squared, does anybody know what this one comes out to? Jonah, looking at this integral, does it make you want to go, oof?
Yes.
Correct!
Let's go.
This is, in fact, oof of x. Because oof is the sound that you look at when you try that you make when you try and evaluate this integral. You can't do it using any sort of nice methods that we have. There is no nice functions that when you differentiate would give you e to the negative x squared. E to the negative x, sure, that just has an integral of negative e to the negative x. But e to the negative x squared doesn't have a nice integral. So despite the fact that we've spent like almost half a semester at this point trying to learn how do you integrate various types of things, there's a lot of functions that you can't do using kind of these nice sort of trying to reverse the differentiation rule sort of techniques. I'm sorry, was that a bit too heavy? Was that a bit too much of a downer? Regardless, Jonah, I'm impressed you knew about the ERF function. ERF shows up a lot in like numerical analysis, by the way. Okay, any questions or comments about factorial, gamma function, any of this doom and gloom stuff I've been spouting for the last few minutes? Dr. Gersler, are you going to quiz us on this? I'm not going to quiz you on this packet, mainly because I don't know what questions I would actually ask from it. Other than, I don't know, compute 6 factorial for me, which, I don't know, it's not really a Calc 2 sort of question written deep down. But I thought this was kind of this is something I thought was kind of interesting, having theorems like this that take these scary looking integrals and relate it to these sort of innocuous things like factorials, which are used in all of these sort of counting problems that show up in math a lot. All right, time for the actual standard 8, where we are going to talk about arc length. So with that, 2, 3, 1, 2. Now you make your way go all the way back, so maybe you can pass one back for back. 1, 2. And a 1, 2. So we have a couple actual standards that we're going to be doing. One this week, one for a couple days after the break. that are related to ways in which we can actually use integrals to help us look at other types of problems in math. Because integrals pop up all over the place in higher level mathematics. I haven't just been teaching you integration techniques just to torture you. That was only a perk. But turns out knowing how to take integrals allows you to solve a big number of problems within the math. And the first application that I'm going to look at with my notes is going to be arc length. So let's say we have some function f of x going from x equals a to x equals b. Let's say it does something like this. If I wanted to ask, what's the arc length of this function between a and b? What does that even mean? Like intuitively. Like, so normally when we talk about taking the lengths of different types of mathematical things, we're usually talking about things that are straight. Like if I told you, for instance, Joy, let's say we have a line segment that goes from -3 to +6. What's the length of that line segment? Yeah. We have ideas for how length works when it relates to lengths of straight lines. Or if I were to ask you 1, 1 and 3, 2 in the plane, what's the distance between those 2 points? You could draw a straight line between them, use the Pythagorean theorem to find the length of that straight line segment. Because it's a straight line. But what does it even mean to take the length of something that's wavy? Because most functions are not going to be straight lines. Well, I mean, there's several different ways to think about what it means to take the length of a segment. The way I usually like to think about it is, suppose we take this function and it's a piece of string. I should have bought in a piece of string. Oh, I have a rubber band. That'll work nicely. Suppose we have this curly piece of rubber band, and it's curly, and I want to know what is the length of this rubber band segment. How would you think to find the length of this piece of rubber band? If you had like a ruler, a straight ruler, mind you, not a curvy ruler. Nora, any ideas?
You could flatten it out and measure.
Yeah, you could flatten it out. You could sort of take this non-straight page and say, hey, I'm going to stretch it, manipulate it to a shape where you could flatten it out, and then use that to, and then once you flattened it out into something that's a straight line segment, then that's something we know how to take the length of, like what Joy was doing earlier. So when we talk about arc length, that's kind of the way I want you to be thinking about how you would take the length of something that's not just a straight line, but something that's curvy. The idea is we're going to take this curvy shape and flatten it out. So let's say we had done that. We took this, we laid like a piece of string or a rubber band or something on top of our function, and then we stretch it out so it's flat. Then finding the length of this flat segment would be what I would call the arc length of the original function between the 2 points, x equals a and x equals b. Usually when you talk about arc length, you're looking between 2 points, because otherwise if I said, for instance, Reagan, find the length of the function y equals x squared. Yeah, doesn't make much sense. You could do it from like -1 to 1, you flatten that out. But if I were to take this function that goes forever to the left and forever to the right, try and flatten it out somehow, how long would that be? Yeah, it'd be infinitely long. It would be, if we tried to take this and stretch it out like that, it would be infinitely long. So when we ask questions of arc length, we're usually looking at function between two specific points. Which, by the way, means that in terms of integration, we're going to be looking at definite integrals when doing these sorts of arc length questions. Any questions or comments thus far? So, doctors, how do we compute arc length? Well, turns out if you want to find the arc length of a function f of x from x equals a to x equals b is going to be given by the formula integrate from a to b square root of 1 plus f prime of x squared is going to be the formula that we have to work with. So for instance, if we wanted to start with something fairly simple, let's say we wanted to find the arc length of f of x equals negative 2x plus 1 from x equals 2 to x equals 5, which in the plane would give us something like negative 4 plus 1 is negative 3, x equals 5 would be at negative 9. Let's say we wanted to use our arc length formula to find the length of this curve, f of x, from 2 to 5. Joy, you look like you have something you're going to say. I must be delirious. So, if we want to use that formula, what would we do? We need to know the integral from 2 to 5 square root of 1 plus our f prime of x quantity squared. So, Joanna, if our function f of x is negative 2x plus 1, what would our formula for f prime of x be? If we were to differentiate that.
Well, it would just be negative 2 plus c. Or no, just like.
Right, just negative 2. No plus c since we're differentiating. If we were integrating, we'd have the plus c. Yeah, if f of x is negative 2x plus 1, a little bit of Calc 1 power rule tells us the derivative is going to be constant. It's going to be negative 2, because line segments like this have constant slopes. And we have to evaluate square root of 1 plus negative 2 quantity squared from x equals 2 to x equals 5. All right, well, negative 2 squared is 4. Add 4 to 1, we get 5. So this is going to give us integral from 2 to 5 of just square root of 5 dx. Sarah, how do we integrate square root of 5?
Can we? Or does it equal maybe a square root of 5x? Or
Yeah, that's exactly it. What function has a derivative of square root of 5? Well, it's just going to be square root of 5 times x. If it helps, you could also think about when integrating a constant, you could write it as square root of 5 times x to the 0. And then if you do reverse power rule on that, you'll get square root of 5 times x to the first power over 1, which is just square root of 5 times x. So we need to evaluate that from x equals 2 to x equals 5. And Aiden, what's that going to give us if we evaluate that expression?
5 times the square root of 5 minus 2 times the square root of 5, which I think we can simplify to 3 times the square root of 5.
Yeah, it's going to be 3 times the square root of 5. Exactly, as our final answer. Fairly straightforward, at least thus far. We have just this, we find the derivative of our original function, plug that in to our arc length formula, and then we can do some good old-fashioned plugging and chugging. So, I have a question. I put a vertical bar there for a reason. Is there another way we could have found the length of this line segment? Using the fact that we know we're working specifically with a straight line instead of with a something that actually has some curviness to it. Nora?
Sorry. So you can use the Pythagorean theorem because you can draw a right triangle and you know the lengths of the line segments.
Yeah, we also, for this specific example, could have used the Pythagorean theorem to evaluate this. That's a right angle or close enough to it. So we could use the Pythagorean theorem and say, hey, we need to know the length of this line segment. Well, that's just going to be the hypotenuse of the right triangle I just drew. Lauren, what's going to be the width of this triangle from x equals 2 to x equals 5? Yeah, so we're going to have a width of 3 to our right triangle. Anna, how about the height?
6.
Yeah, we're going to have a height of 6. And if we call this c, we'll get that c squared is equal to 3 squared plus 6 squared, according to the Pythagorean theorem, which is equal to 9 plus 36, or 45. And Kate, if c squared is equal to 45, what does that imply c would have to be equal to?
The square root of 45.
Yeah, c would have to be equal to square root of 45. Do we need a plus or minus?
No, because you can't have negative length.
Yeah, because you can't, yeah, technically, negative square root of 45 squared would also give us 45, but in this context, it doesn't make sense to think about the length as being a negative value. So we're not going to include this item. But how did we get 2 different answers? Bethany?
So you can write 45 as 3 times 3 times 5, and then you can factor out impurities outside of the radical sign. You can just do 3 times the square root of 5.
Yeah, we can pull this apart, use the fact that 45, well, it looks like it has a decimal point there. 45 is just 3 times 3 times 5, which means we could break this up into square root of 3 times square root of 3 times square root of 5, which gives us the same value in the end of 3 times square root of 5. It's always nice, if you ask me, when we come up with new formulas for things, if our new formulas kind of match up with, give us the same results as old ways of working with things. And this would be a case where, whether we want to use our arc length formula involving some integration, or just use some plain old-fashioned Pythagorean theorem, it'll give us the same answer either way. Any questions or comments about this example? Kate, could we have used the Pythagorean theorem? Well, if we had known maybe what formula for our f of x, could we have used the Pythagorean theorem to find the length of this curve as opposed to the one we just did? No? Are you sure about that? What if we had...
If you're like infinitely small ones.
Ah,
That, but I mean,
infinitely...
not like in the same way necessarily that we did that one.
Yeah. So what we could do, if we wanted to try and, do I have yellow? Yes, I do have my yellow chalk. To find this using the Pythagorean theorem, we could approximate this by taking tiny little line segments and saying that the length of the curve should be approximately equal to the number of line segments. In fact, if we were to have more and more line segments, have more and more points, like splitting it up to like this and doing like instead, the more line segments we have, all of which we can compute using the Pythagorean theorem, the more accurate our line segment approximation would be to the actual arc length. And so one way we could think about computing the arc length is if we have infinitely many of these little line segments that we're adding up. And we're adding together these infinitely many small little areas. But adding up these infinitely small little areas, I mean, that's not the same as taking an integral. Is it? So, for those of you who had me in Calc 1, do you remember how we originally defined the definite integral? It wasn't using fundamental theorem of calculus, antiderivative at b minus antiderivative at a. Ty?
I remember that we filled in the curve with rectangles, and so it was infinitely many rectangles.
Yeah, the whole idea behind definite integral is you have these sort of infinitely many rectangles to find area under a curve. Where we were basically summing up, taking a sum of rectangle areas. Turns out, Dr. Gerstle, where does this formula come from? Well, where it actually comes from is something very similar. We're basically adding up the lengths of infinitely many tiny line segments. And that gives us, in the same way that doing this sort of Riemann sum back in Calc 1 gave us a definite integral formula like what we're used to working with using the fundamental theorem of calculus, it turns out in Calc 2, adding up the lengths of these infinitely many little line segments, you can represent using a definite integral. That's what the definite integral means. It means adding up infinitely many tiny little things. So actually, technically, Kate, when we do this integral, we are, in fact, doing the Pythagorean theorem infinitely many times. That was a little bit of a trick question I asked you earlier, though. I apologize for that. Not really, but I'll pretend to apologize for that. So where does this formula come from? Well, if you look at square root of 1 plus f prime of x squared, the whole idea is if we have a line segment of length 1, and our curve has a slope of f prime of x, the height of that line segment should be equal to f prime of x. If it has a width of 1, the height should be f prime of x. And so if you take square root of 1 plus f prime of x squared, that's actually just going to give you the length of the hypotenuse of that line segment there. If we labeled this side as c, we get something like c squared is 1 squared plus f prime of x squared, which tells us c would then be equal to the square root of 1 squared plus f prime of x squared, which is same as 1 plus f prime of x squared. So that's kind of where that formula comes from. Like where does the square root of 1 plus f prime of x squared formula come from for computing arc length? It actually comes from using the Pythagorean theorem technically an infinite number of times. So the fact that we got the same answer using Pythagorean theorem here as versus there, I assure you, is no coincidence. It's just that in this case, this is a relatively simple problem in that if your curve is just a line segment to begin with, you only need to use the Pythagorean theorem once, as opposed to the infinitely many times you need to use it if you had a more curvy curve, so to speak. Any questions or comments before we look at another example of putting this into practice? Yeah, Bethany?
Why is the y value f prime of x? Why wouldn't it be of the hypotenuse value?
Good question. It's because of how you think of when we think of f prime of x, we are thinking of slope of tangent line, right? So what do we even mean by slope in the first place? Well, that's going to be rise over run, or change in y over change in x, at least in an intuitive sense. That's kind of how slopes usually originally defined back in Calc 1. So if we're saying that our change in x is going to be equal to 1, then f prime of x is just going to be the change in y over 1, or change in y by itself. So that's why we would say that, I'm doing a little bit of abusive notation here, but like if the function, let's say, had a constant slope from a to a plus 1, let's say, if the change in x is 1, the change in y would automatically be equal to f prime of x. Yeah, good question. Sorry, I kind of just glossed over that earlier. Anybody else? Oh, Dr. Gerstle, we're old hat at the Pythagorean theorem. Why are you giving us this crazy formula for something we could just do the Pythagorean theorem on? All right, well, if that's your attitude, prepare for this. Let's look at another example where this time, instead of integrating a linear function, where's my notes? Let's integrate. G of x is 1/4 x squared minus 1/2 natural log of x over the interval 1 to 2e, which is about 5.4. So if we graph this function, we end up getting a curve that looks something like that. From say x equals 1 to x equals 2e. Well, with something like that, we don't necessarily know, we can't just use a single Pythagorean theorem to find the length of the curve between these 2 points. Why? Because it's curvy. If we had a perfect graph, we could lie out a piece of string on the graph and then go boing, stretch out the piece of string, and then use a ruler or something to measure the length of that string. That should give us the arc length. But, Katie, is that a perfect graph of that function, do you think?
Probably not.
Say what?
Probably not.
Probably not. It flatters me that you're saying probably not instead of no, Dr. Gerstle, you cannot possibly accurately draw that function to 100% accuracy. But I can tell you for sure, no, that's not a perfectly accurate graph. It looks approximately like that. I looked it up before class. So we can't do our piece of string method without a perfect graph and a perfect measuring ruler and perfectly steady hands, like we're the world's best surgeons to work with. So instead, we're going to have to do our process of doing an infinite number of little Pythagorean theorems. Or, because doing an infinite number of anything sounds hard, we can equivalently use the fundamental theorem of calculus and evaluate this definite integral. So before we do anything, we're going to need a formula for g prime of x. Emerson, how would you differentiate this function?
Well, I would do it in pieces first. So 1/4 x squared with the power rule is just gonna be 1/2 x.
Okay.
And then 1/2 times the natural log of x, we have the derivative of the natural log of x is 1/x, and 1/2 is a constant, so we can take it out before we take the derivative. So it's just 1/2 times 1/x or 1/2x.
It's going to give us 1/2 x minus 1/2 times 1/x. Or we could also write this as x over 2 minus 1/2x if we want. A lot of ways you could write that out. So if we want to write our arc length then, our arc length is going to be an integral from 1 to 2e, because those are the two x values we're given. We're trying to find the length of the curve between. Our square root of 1 plus g prime of x quantity squared, which will give us the area from 1 to 2e under square root of 1 plus x over 2 minus 1 over 2x quantity squared. All right, James, I need your help. How do we square this expression?
So it's x squared over 4.
In other words, what are we going to get if we do some FOILing here? We get x squared over 4.
Yeah, and then it's minus 2 times 1/2x times x over 2, which we can just multiply that out later.
Minus x over 2x squared. Let's say if we did the inside two terms. Or no, not 2x squared, 4x. Gosh, why did you let me say otherwise? Okay, how about the outside two terms?
Then it's x over negative x over 4x.
Oh, hey, that's nice. We got two of the same thing. And the last two terms?
Then it is plus 1 over 4x squared.
Yeah. Well, doesn't that look like a lovely expression to try and integrate? Devin, how can we simplify x over 4x?
X over 4x, just integrate.
Oh, we're not trying to integrate anything, just how do we simplify? Because I think we could write this in a nicer form if we cancel out x's in the top and bottom. So what would we get if we canceled out x's in the top and bottom?
Just make it 1 over 4.
Yeah. So it turns out this is the same as negative 1 over 4. Also that term for that matter. So we end up with something like 1 minus 1 over 4 minus 1 over 4, which I'll move over here, is going to give us integral from 1 to 2e square root of 1 plus x squared over 4 minus a fourth minus a fourth plus 1 over 4x squared dx. Allie, what would we get if we combined our three constant terms inside the square root?
Positive 1/2.
Yeah, 1 minus a fourth is 1 minus 2/4, which is the same as 1 minus a half, or 1/2. So this will give us integral from 1 to 2e, square root of x squared over 4, plus 1 over 4x quantity squared, plus a half. And unfortunately, I don't think there's a super nice way to simplify further inside the square root. Holy moly. How do we evaluate that integral? Nora?
Can't you just use U substitution?
Okay, what would your U be?
Couldn't you make it the whole expression inside of
Okay, so Nora, you want to try a U equals x squared over 4 plus 1/4 x to the negative 2 plus 1/2, which would take the stuff inside the square root into square root of U. That would give us a du is x over 2 minus 1 over 2x cubed dx. And so, Nora, how do you propose we deal with the x over 2 minus the 1 over 2x cubed expression?
Can you just divide it up on both sides?
Sure, okay, so replace dx with du over x over 2 minus 1 over 2x cubed.
That would help you.
That doesn't sound helpful. That just sounds a way to take our initial integral and make it something even scarier. It's a good idea, Nora, but unfortunately, the changing dx to du part makes U sub not super helpful on this one. So I don't think we're gonna do that. I'll be honest though, that's the first thing I tried as well when I looked at this problem. Okay, we can't do U sub. We can't do integration by parts. Well, we could try, but I'll just tell you it's not going to get us anywhere. Partial fractions is right out. Inverse trig function, oh gosh, that almost looks like an inverse trig integral, but don't worry, it's not. So how do we evaluate this? Emerson?
Would it make it easier if we made everything into one bigger fraction? So like, because we have, so for each term, we see that the biggest denominator is 4x squared. So you take x squared over 4 and multiply it by x squared over x squared, and take 1/2 and multiply it by 2x squared over 2x squared, and then we get like one. Would it be easier to work with like one bigger fraction instead of 3 small ones?
Okay, do something like this. Write it as square root of x to the 4th plus 2x squared plus 1 over 4x squared.
I just wonder if that makes it easier to like manipulate it all.
I don't know, maybe. I'll say this, I thought it was worthwhile enough to put it up on the board. And I think that's a good idea. Okay, does this look any easier to work with? I don't know, maybe a little bit. James, do you have an idea?
You could square the top and the bottom, since the bottom it has an easy square root.
Oh, split it up into square root of top over square root of bottom? Okay, that sounds like a good idea. Take square root of x to the 4th plus 2x squared plus 1 over, well, that'll just be 2x. Because square root up, using here that 2x is equal to square root of 4x squared. Okay, progress. Looking a little bit nicer, a little bit easier to deal with. All right, Aiden, do you have any ideas?
I believe our top polynomial is a perfect square, so I think it can be x squared plus 1. We take the square root.
Ah, now there's a thought. So you're saying we could write this as integral from 1 to 2e of square root of x squared plus 1 quantity squared over 2x, like that?
Yeah.
How does that help us?
now we're able to solve the square root, so we get x squared plus 1 on the top and then 2x on the bottom, and then I think we can do, like, might be able to use up, maybe not.
I like it. So yeah, actually Emerson, I think your idea panned out nicely, because when we combine everything into a single fraction, like here, we get a denominator that's a perfect square, and then we also get a numerator that's a perfect square. And we can cancel out the square root and the squaring to get integral from 1 to 2e of just x squared plus 1 over 2x. Well, that looks a lot nicer. We've managed to eliminate the square root entirely. Okay, so where do we go from here? Still doesn't look super easy to integrate, although it does look a lot easier than what we started with, or at least in my opinion. James?
Break it up into a standard 1 problem by making it x squared over 2x plus 1 over 2x.
Split up the fraction, in other words. Okay, we can do that. Integrate from 1 to 2e, x squared over 2x plus 1 over 2x, which is the same as integral from 1 to 2e of, what, 1/2 x plus 1/2 x to the negative 1. And now I think we're finally ready to actually evaluate our integral. Right. Doing a lot of jumping around on the board because I can't decide where I want to actually write this. So, Gabe, how would you integrate 1/2 x plus 1/2 x to the negative 1? Because I think we're finally ready to take some antiderivatives.
1/2 x would be 1/4 x squared.
And we get 1/4 x squared. How about the 1/2 x to the negative 1?
Plus 1/2 natural log absolute value of x.
Yeah, that's plus 1/2 natural log absolute value of x. Hey, look, we did it. Well, other than plugging in our bounds and subtracting. Because we still need to plug in 1 and 2e at this point and subtract. Jonah?
Is there a reason why this is the original formula?
1/4 x squared plus 1/2 natural log of x?
Yeah.
It is not the original formula. That one has a minus sign.
Yeah, that's right, never mind.
Plus this one has an absolute value. Although between 1 and 2e, the absolute value turns out to not mean anything. Or not change anything, I should say. But yeah, that does look pretty but other than those two things, yeah, that does look pretty similar to the original formula. Alright, now we can do some plugging and chugging. If we plug in 2e, we'll get 1/4 times 2e squared plus 1/2 natural log of 2e. 2e is positive, so absolute value of 2e is just 2e. Minus, if we plug in 1/4 times 1 squared plus 1/2 natural log of 1. This will come out, let's see, 2e quantity squared is 4e squared, which over 4 is just going to give us, I think, e squared. Plus 1/2 natural log of 2e minus 1/4. Katie, what's natural log of 1?
Is it, I don't know why I got this. The E? Or no, that's not
No.
correct.
I'll ask you this. Let me ask you an equivalent question. E to what power is going to give you 1?
Maybe 0?
Yeah, so natural log of 1 is 0 because e to the power of 0 gives us 1. Doing our e to the x natural log of x, swapping x and y values thing. So that's 0. That goes bye-bye. What's natural log of 2e? Holy moly. I think here we could be a little bit sneaky, use some log properties to say that's going to be natural log of e plus natural log of 2. Here we're using the property of logs that says natural log or any log of a times b is the same as log of a plus log of b. Split this up into 2 times natural log of 2 times e is the same as natural log of 2 times plus natural log of e. Nora, what's natural log of e? Yeah, because e to the power of 1 is equal to e. So this is 1. So I think we're going to get e squared plus 1/2 plus 1/2 natural log of 2 minus 1/4. And then for our final answer, we're doing great. For our final answer, we're going to get e squared plus 1/2 natural log of 2 plus 1/2 minus 1/4 will come out to plus 1/4. So I got this. There you go. That is the length of the original curve from x equals 1 to x equals 2e. Believe it or not, that integral is just a standard 1 integral. A really, really mean, nasty, sneaky standard 1 integral. But we didn't need u sub, or integration by parts, or partial fractions, or we didn't actually do anything that complicated in any one individual step. It's just that I think the combination of steps on this one was, there were just a lot of steps that we needed to do. Alright, that's going to do it for today. When we come back on Friday, we'll do some more practice playing around with integration, I said integration by parts. I got that on the brain now. We're going to play around with looking at some more arc length integrals and talk a little bit more about what are some circumstances where finding arc length might be nice. Like say, proving that the circumference of a circle, the radius r, is 2 pi r. Hope you all have a good one. See you all on Friday.
Dr. Crystal, do you think I can take a retest of standard 6 to 4th class on Friday?
4th class?
Yeah.
Sure. Yeah, if you just want to come by at like 7:30 or so,
Okay.
I'll get one for you. Okay. That's all. Okay, thank you. Take care.